that it is my pleasure to introduce the speaker for this evening. I personally got to play around with Hadoop, which is one of the projects that Ted works on over the past year or so. I'm not a math guy, and that project has been kind of the introduction into data science for me. And one of the amazing things for me is that it's made data science approachable. Anything I found on the internet outside of that got me pretty deep into feeling like I was back in college being confused in calc again. This is a set of libraries that Ted works on that made the stuff that you hear about, these types of analytics and whatnot, approachable from a plain Java developer like myself. I'm not sure how much I can actually cover that tonight, but in general, what he's working on is pretty cool, and it's my distinct pleasure to introduce Ted Dunning.
That microphone sounds live now, so I just leave it to term live, I guess. That was the highest compliment I've heard in a long time, because I think that math is really exciting, really, really beautiful, but it often is conveyed really, really awfully, and conveyed in a way that's really abusive and makes it hard for people to see how nice it is, to see how much fun it is. And so what I'm going to do tonight is another example of math done that way, in an approachable way, where the concepts behind it are actually just really, really neat, and really not that hard to do. And so there's going to be some math in there. There's going to even be some Greek letters, but you can squint, pass over those details, or you can have the details if you like. But the idea behind it, the shape behind it, should still be clear. I'm going to talk about anomaly detection. What is it? You know, that sort of thing. I'm going to give some examples. I'm going to generalize it. That's really the mathematical behavior of all. I'm going to go philosophical on you, talking about how compression is truth. Wow, man. That's the correct answer to philosophy there. Wow. And we're going to talk about deep learning, and then why this all matters for time series. I'm Ted Dunning, like the guy said. I work for MapR, the guys who give me the cool hats. And I've also worked a long time on open source software. And I still do, because MapR is largely an open source company. Work with Apache, Mahout, Drill, Zookeeper, Spark, many, many others. I mentor projects and also work on them. So Storm, Flink, I think there's 5 or 6 that I'm mentoring right now. MapR makes what I call the leading technology for Hadoop. It is Hadoop for the most part, but it adds a considerable amount of technology, which makes it work better in business situations. The stuff I'm talking about tonight is also in a little bitty book. You can see my co-author there, that's Ellen Friedman. She's a world famous hand model, so you can see her thumb there. That's about all you're going to see of her tonight, but you'll see her again at Strata. We'll be signing books. You can get a copy of it PDF-wise from the MapR website, if you don't mind typing that in. Or you can send me email, and I'll set you up. So let's talk about anomaly detection. This whole field, my interest in this field, comes from my personal experience. I had a position at a company. We sold software online, and we had a hyperactive CEO. He would call me at 2 in the morning, and he would say, Ted, we haven't had any sales for 5 minutes. Is that okay? What do you say? I mean, your CEO calls you at 2 in the morning and he asks you a question like that. So you say, you're not awake. You can't tell what's going on. You don't know what's right, what's wrong. And so what I really wanted to do there, and what we did do, is we built a system that told us about any sort of fault with the sales process about 5 or 10 minutes before it turned the dashboard that Dennis looked at red. And so then when he would call, I would say, yeah, Dennis, I've been on this for minutes. What's the problem? You didn't notice until now. And this very quickly built a sense of confidence that we would find problems before he did, and we would always find the problems before he did, and never have a situation where he would find a real problem before we did. And this is very important because it's an evolution in a CEO's life. You have to get them to where they sleep through the night. It's very important for their further development and also for selling the company. And we did well out of that. But that's the key there, is we had to find out what the anomaly was. But of course, figuring out whether or not the sales system or anything is broken isn't easy because things are changing all the time. You change the system, you change the pricing, whatever. You have to decide what is normal. So that's the essence of anomaly detection, just finding out what isn't normal. Even though you didn't really know what normal was yet. And you certainly didn't know what was important to talk about. But don't wake me up if it's not broken. Do wake me up if it is. And no, I don't have a definition of broken. So let's look at it here. This is a signal. It's actually random numbers that I made up. And you get an impression there. I mean, normal is kind of bzzz there around the value of 0. Quickly get an idea there. And looks like an anomaly there, that bump. Or on the other hand, if those happen all the time, maybe the step here is the anomaly. Okay? The basic idea is what you've done in your head here is you looked at the first page and you said, that signal kind of muddles around there. It's no big deal if it goes up and down a little bit. It does that all the time. But then it did something different. And as I said, maybe the spikes happen periodically, in which case that should be incorporated in your idea of normal, even though it's not a normal distribution, the Gaussian sort of thing. Normal is what the system does. It isn't based on any mathematical prior expectation necessarily. It is what it does. And then anomalies are what it doesn't very often. So we want action when it breaks. We want inaction when it's not there. We usually actually have a budget for how many problems we can look at in a month or something like that. So we probably want to get that many alarms. First of all, we don't want the alarms to never go off because then people will forget about them or they won't carry the thing. We want them to go off just to keep people practiced up on it. We want them to go off up to our budget so we find as many problems as we can. Now, of course, we want those alarms to be as much as possible when the problems do occur, but we probably want to go up there. So what we want to do is look at the signal, do something like a percentile calculation, and say whatever number of calls we can absorb, let's adjust it so a normal signal will give us that many calls. Now, we can build a system like that. You can build an online algorithm to find out what percentiles, what the whole distribution is, and you can use that to set the threshold. And that's pretty cool because it automatically has all of the statistical properties that you want. It's as good as it gets in terms of finding that anomaly. Mahout already has it. Streamlive already has it. You can get it off your, off GitHub. We're done. 9 slides. That's not the end. You can get software that does that, and universally it's recognized this really isn't the answer because you're looking at thousands of signals. And if you get 1 out of 1,000 alert on 1,000 signals, you're kind of getting alerts all the time, even when those things are relatively normal. And even worse, with a signal like this, you'll find the signal at A because it sticks up above everything. But you're going to miss the signal at B because it's hiding in the valley here. So a simple threshold is just absolutely not the answer, even once we go to this slightly more sophisticated problem like this. So we need a fancier model that says during the night it goes down, during the day it goes up, night it goes down, day it goes up. So that then this is anomalous, it's above the model. Here's another example. You see that spike there? Now it looks like kind of a complex signal, but there's this long baseline with this big anomaly here. That's actually not an anomaly. It's a heartbeat. I consider those normal. Not everybody does. Some people seem to exist without them. But what an anomaly looks like in that signal is that. This still fits what we're talking about. We have this model. We have this idea that heartbeats, have the P, Q, R, and S sort of pieces. These are the QRS things, the big spike and the thing just before and after it. And then there's other parts of the waveform. We have a model of that's what it looks like. And pretty quickly, when we look at a single person, we understand how quickly their heartbeat happens, what exact shape they have based on exactly where the electrodes are and which beats of the heart are still alive. And when it suddenly goes faster here and much slower there, we know that's not normal. So this idea of model of normal, and then anomaly, is a really good one. So for simple signals, we can just say, oh, it's the normal distribution. For fancier signals, or for the real world, which is always a nice thing to have work, we have to do something fancier. And here's one example of how we could actually build a model that works on heartbeats. What we're going to do is take a window. This is a window function. It's 0 almost everywhere, except where this little bump is. We're going to multiply the original signal point by point times this window, and that gives me just this little piece of the original signal. It's pretty easy. That's a hand window. That's just sine squared. There's nothing fancy about it. But the nice thing is, if you offset it by half and add it to the next offset sine squared little bump, they add up to 1 during that range. And if you keep it shifting them by half of their width, they'll add up to 1 across that. What that means is that this lower thing, when we shift this across, if we add up all of the little piece of signals that we get down here, we'll get back to the original. It's really kind of cool. And we can process those independently, so that if every one of these little windowed signals I can approximate well, then practically by definition, when I add those back together, I get a good approximation of the original. It's a nice, easy way to make a model one window at a time. And the window, then, of course, we scan across the data like this. And each time we do it, we do the multiplication, we see a different piece of the signal up above. And then sometimes, see, that looks a lot like that first window. It's very similar. And if we keep scanning across, we see another one that's a lot like the first window. And another one. So we could then cluster all of just the windowed versions of these. And that would let us approximate it. We just take whichever cluster is the shape that's closest to the window we're looking at and scale it and put it in. Go to the next window, find whatever shape is closest to what we're looking at, scale it, stick it in. And so what we get then is, through the clustering, we get a dictionary of shapes. These are the shapes that heartbeats are in this window-sized chunks. It's kind of cool, because that is a dictionary of, in some sense, the meaning at a very low level of heartbeatness. And new signals then could be encoded if they are heartbeats like the ones we've seen so far. This is a really simple model, and it allows us to do that. Here's a picture of the first 64 of these common shapes, and you can see in there variants. See there, and there, and there. These are shifts of that first signal that we saw. Of course, it's a very fixed window step, so it has to have several shifted versions of each shape in there. But it's really, really a simple way to build a model. And here it is in action. The top is the original signal. The middle, I'll even point this side for a little bit. The middle is the reconstructed thing. You can see they look almost identical. It's probably hard, in fact, looking at the projection to see any difference. But maybe you can see just a little bit of fuzz in this signal that isn't on this signal. The fuzz, the noise, doesn't repeat naturally because it's from a different source. And so when we do the averaging that clustering is, the noise gets pulled away. It's like pulling lint off. You could actually imagine that this, in some sense, is the more true signal. And down here, if we look at the error between these two, it stays pretty small. Less than 50 units almost always. Until we find an anomaly. The anomaly occurs right here, not where I push the arrow, where we get a spike in reconstruction error. Now, it's really hard to see. This pulse right there, the one just to the right of the arrow, is different. And you can see on the reconstruction really looks different. If we magnify that, you can see why. The pulse that's not reconstructed is actually a double pulse. And the reconstruction has never seen anything like that. And so it can't really reconstruct it. There's never been a pulse next to a pulse in its experience. Certainly it hasn't been often enough for it to have devoted some of the dictionary to that. And so it says, just like I do in the middle of the night. That's the way it says, and it's unable to reconstruct the signal. And so the reconstruction error then is big. And it's just like that first case where we had going along and then a spike. Here we have a signal right around 0 that sits close to 0, and there's a spike. So we can say that's an anomaly using that original kind of detection, just that adaptive threshold. Now there's a model up above that which is saying this is what the shapes actually look like. But all we have to do the thresholding on is the reconstruction error, the degree of anomaly. We don't really see this much anomaly, bam, we just see a big one. So this is a really easy way to do this. This was like 3 hours on a Saturday afternoon. It really wasn't a huge amount of thing. Here's another anomaly. This is something that happens when a lead comes loose on an EKG or a person moves and they shift a lot. And this looks nothing like a heartbeat. And so the heartbeat model is unable to express it. It's not a thing that it can demonstrate. And so the anomaly is astronomical. Of course, that is an anomaly. The first one is a physiological anomaly. The second one is a data gathering anomaly. The system can't tell the difference. It doesn't know one anomaly from another. We can make that decision, but it can't. All it can say is, this isn't a heartbeat. This really isn't. So we can build that. We can take the model that we have here that's reconstructing the signal, subtract it off of the signal, and then put that thing that we had earlier, that adaptive threshold. We've got a new kind of anomaly detection there. Well, not new, it's new for this little show, but not new to the world. People have done this before. This just happens to be a very nice, simple example of it. Now, if you think about this, and if you actually draw back to the real mathematics inside here, this model delta, the delta meaning difference. The model delta anomaly detector is a sum of two random variables, one of which is very structured and looks like heartbeats, and the other one is just this uniform noise, the reconstruction error. And so the difference then is actually, interestingly, the measure of probability. It's the inverse of that. And the size of that, small anomaly means high probability. Large anomaly means low probability according to this model. And if we think about probability distributions, the original signal had a very simple probability distribution. It's near 0 with some noise around that. This one has a slightly more interesting probability distribution. And if we take that idea of building a probability distribution and looking for deviation from it, subtracting in some sense, we can build this into a whole general family of ways of building anomaly detectors. And they're able to find heartbeat irregularities, people not buying stuff on a website, speed variations. They can detect all kinds of things if we can build that model. Let's talk about the website example. The idea is that people are coming in independently. They don't normally talk to each other and then come in. So the model is what's called Poisson. It's a distribution of events in time where they all essentially arrive independently. And that means the difference between the times has a very nice, simple, exponential distribution. Now, the key problem in the real world is this idea of a Poisson distribution where it's completely independent of time is not true. People come more at certain times of day than at other times of the day. They come more at certain times of the world than at others. I did in the little book, I did a nice study of how often there were visits to the page for Christmas on Wikipedia. And looking at it in November, you get this very sharp, nice pattern of weekday, weekend, daytime, nighttime. That's a very US English-speaking centric concept, and so it is focused around kind of our time zones, because we have the largest probability mass of English speakers. And so you can see that, and then through Thanksgiving week, it drops, and you can actually see it on Thanksgiving Day. It stops at about noon Eastern time. It's like when everybody starts eating. It's just fantastic that way. And so you can actually see all these features in there. But then, as you go through December, it goes crazy. The volume of those visits to the Christmas webpage go through the roof. And on the 25th, it collapses. So can we build a model to predict that? And yes, indeed. These techniques can do that. And the idea is that we just have to model that frequency and then scale the time difference between arrival times, and we have that anomaly signal. The prediction is 1 over the rate. That's when the next thing should be. And the actual value, or more likely, the log of that value, is our probability indication. See, Greek letters. Ooh. So we have the idea that the time between these things should be exponentially distributed with that rate thing there, the mean time actually. And so the probability that's greater than a certain time is that exponential. And so the log of that, just like we had in other cases, the log of probability is this linear function of the inner arrival time, scaled by our expected time. That's pretty cool. Or that is a rate. So here, for instance, are actual inner arrival times. And you can see they have that nice fur along the axis look of it. And we can use that first detector all over again if we can find out what lambda is. And if we know what lambda is, these inner arrival times will be fixed all the way across. It's really kind of exciting. So here's just giving you several examples of how we can do this with a probability model. Why minus log p is a good way to convert to an anomaly measure, and also how to build an adaptive anomaly detector. So different systems, of course, require different models. Continuous systems need continuous models. Events in time need to do something like subtracting times. We can do events with labels, and if we have a model where sequence is the important thing, we can build a probability model there. But this works precisely because of one wonderful philosophical thing, and that is the compression. And we're measuring compression here because when we do this log probability, which I thought was on this slide, but it's not. When we do the log probability, we're estimating how big the compressed representation would be. Size in bits is inherently a log-ish thing of the number of things we're encoding. If we want 4 things, log of 4 is 2. It's going to take 2 bits. So the log of the probability is a measure of how large the compressed representation would be. That's the whole thing with entropy, is how that works. And therefore, a small compressed size means we have a good model in terms of anomaly. And in fact, when we make the log make the compressed size as small as possible, make the log probability as minus log probability as large as possible, we have found the correct model. This is a very cool result, that where we found the best compressor, we've actually found the best model. Now, it is unfortunately not computable to actually find that exact correct answer. But for many cases, we can come very close. And that's the cool thing here, is not only does this turn out to be a nice heuristic, but it actually has a real meaning underneath it, that this is, in fact, roughly the best that you can do in terms of anomaly detection. It is the best model that you can build. Minimal error is maximum likelihood is maximum compression. So the reason, never mind. I will go into that if we get a majority of people who want to see that. My guess is we won't. But it's in the slides so that anybody who wants to download it can do that. Usually it takes a little time to go through that, and so it's not real appropriate for an evening sort of talk. But it is an amazingly simple little walk through there. And it's all about the way logs, this is a graph of log, is always less than the line with slope 1 and the right offset. That's all it takes to know that this universal truth about models holds. So that's exciting. Now, there's another way to think about this. And if we go back to the EKG, we were taking the input signal, we were encoding it, and then decoding it. The encoding step is selecting the closest cluster and getting a scale for each time step. The decoding is taking that cluster and scaling it and then adding them up. Encode, decode. The encode is the compression operation. The decode is the decompression. So we were building a system like that, where we had the original, the encoder, the decoded version of that, the reconstructed signal. We subtracted the top and the bottom to give us reconstruction error, which is an estimate of probability. But this idea of an auto-encoder, an encoder of a signal into itself again, encoded, decoded in the same step, is one that's taken from the neural network literature from time immemorial. Because before there was dirt. All we had was rocks then and neural nets. And so this idea is really kind of a cool idea. But the thing that we had there, the clustering that we had, is in fact a neural net. Didn't look like it. It looked sensible and reasonable. But in fact, it was a neural network. The idea there is, I should not look down. The idea there is that the input signal there, we find the closest cluster. And we do that because they're all normalized by doing dot products. That means just the sum of the weights in the cluster times the corresponding signal values, and we add those sum of products together. And the largest one of those will be the closest cluster. Simple geometry. The dot product is the cosine of the angle. And normally we're looking at the sine to find the largest sine, or the smallest sine. Sorry, the largest sine, which is the closest. And so we can optimize either the cosine for one thing or the sine for the other. Sine and cosine work together. And so dot product, biggest dot product finds us the closest cluster. And in the neural network, the way it works is the input signals samples are up here. Each time they cross one of these lines, they get multiplied by a weight. And when they arrive in the middle here, those values are added together. That's just the notation there. So that's doing a dot product. And so all we needed to do is have this hidden layer be designed so that only one of these can be activated. And it'll be activated by the amount of its dot product. And now these lines on the bottom here have the same values as the ones on the top because it's an autoencoder. We're running it backwards. And so what it's doing is multiplying the value here times the weights, and they pop out here. And so it's selecting the nearest cluster and putting it out with that weight on it. And this 1 of k type of thing is a simple kind of neural net. So this cluster-based regressor is in fact a neural net, and that lights into an interesting thing. We have one hidden layer there, which is a 1 of k type of thing. We could have generalized it by saying it could be m of k, maybe 3 clusters, pick the 3 closest and add them up. And we'd have to learn the clusters a different way. We could have done that. We could have done a couple of different things, but the sparsity there, meaning when we only have 1 of 100, 1 of 400 clusters, is an information bottleneck, which is what autoencoders are all about. And so we take our time series input and our reconstructed time series, and we shift that little neural net across time, like that. And each one of those then reconstructs one window. But what we could have done is taken several of those windows. Those are at the top here. That's one of those original neural nets. And there's another one, and it's just encoding. Its pair is down here. But then from this window's encoded signal and this window's encoded signal, we could do another autoencoder, a second level of autoencoding, which now sees a broader range and is now looking at these higher level features, like this kind of spike, that kind of bump, this kind of nothingness, refractory period. Now it's going to say, when I see the 3 of those in sequence, I think it's a this kind of thing. And then it can reconstruct down here what signals it saw, or which patterns it saw, and finally the reconstruction there. And the idea is that if we add more and more of these layers, we're learning higher and higher level features, more and more global features. So the windows that we have right here, oops, he's got 5 fingers up, we're gonna have to talk faster. We're gonna go faster.
No, it's not time, I have a question.
Oh.
For inputs in these neural networks, is that with the time series, is that XY cores? What kind of inputs do you usually put into these encoders?
Well, it very much depends on what we have.
Okay.
And
for time series like the EKG that you...
EKG was the actual signal strength.
Okay.
Now, these were Holter monitors, which are 24-hour monitors, and those are usually only 2 signals. In a full medical in-clinic EKG, they have 12 signals. It's 12-dimensional. Or if you have something else, say you have a municipal water system, you have flows and pressures, thousands of them. If you're buildings, then you're measuring temperatures and consumption, or if you're looking at, in a chemical plant, you've got, thousands and thousands of pressures and temperatures and things like that.
Okay, so would each output, since it's a window, would each output specifically be a strength at a point in time, or
Well,
do you
in
just
this
keep
case,
moving
in the
along?
EKG, it was a value.
Okay.
And it's going to reconstruct exactly what it was. But the reason that we looked at 32 values at a time is because what we were doing is reconstructing the idea of the dynamics of the heart. But we can't see all of the dynamic variables, so all of the electrical signals that are causing muscle and elasticity and pressure and energy storage that's in your heart. You can't see all those, you can't measure them, not
Sure.
if you want to survive. So what we have to do is we have to reconstruct the space of all of those measurements. And we do that by taking successive samples.
Okay.
That's called state space reconstruction, which is kind of like a concatenation of the words I just said. But it's reconstructing that space. And if you have good measurements, you really can reconstruct the state space. Now, if they're all from the same angle or something, you can't. But in a lot of systems, you can. Now, other systems, like the water system, you can non-fatally measure all of those values, or at least most of them. So there you have direct access to the state space, so you probably don't have to do the windowing. Not as much anyway. And you just look at all the values right now, and those tell you all of the energies and momentum terms in the state of the system. So you'll either look at a sequence of things, if it's a time signal, and you have to reconstruct state space, or if you can measure it, you'll look at it directly. But either way, you will try to reconstruct your measurements. If it's an image, these might be pixels. If it's sound, they might be signal intensity.
Yep.
It might be pressures and flows in the appropriate system.
Okay, so you're fitting to the data that you have.
This is totally specific to the data you have. as all data analysis should be, because we're finding out what's specific about this system.
Okay, cool.
Yeah.
And in case you're curious, you still got about 30 minutes of time. So
I'll talk slower. Okay. But anyway, the idea here is that we have a little bit of abstraction here as to which kind of shape it is. That's in the first clustering. But then by looking at which shapes occur in sequence, we can get a higher level of abstraction. And we can build a system called deep learning. That's deep because we're stacking these things end on over this. And over the last 5 years or so, this style of system, not necessarily with the clustering each step, but with simplified learning laws and very deep neural nets, has had dramatic advances in understanding signals. So anybody here with an Android phone, I would guess there is. The speech recognition on Android is now based on deep learning. It no longer does feature extraction like Fourier transforms. It looks directly at the sound levels and learns its own feature extraction, learns what sequences of those features mean, and ultimately what words the person said. It could just as well go back and auto-encode and reproduce the speech if it were appropriate, and that would be a nice anomaly. In fact, if you had one speech detector which is totally trained on English speakers, if you gave it Russian speakers, it would show a high reconstruction error, because the sequence of phonemes and even the phonemes themselves are not quite what it learned. It would find anomaly in that. You can actually build language identifiers in this way. And likewise, you can do that with images. You can say, what's wrong with this picture by these techniques. So it's a very, very general form of anomaly detection, all based on this idea of building a model. Now, yeah.
It occurred to me that one possible application of this, you could have a security cameras watching an airport and a computer spotting a terrorist based on how he's moving around. But I think the problem there is simply getting good data in the first place. You have to have maybe a couple thousand terrorists go through the airport so you learn how to spot them. How do you get around that problem?
Well, that problem is exactly the problem that anomaly detection is designed to deal with. This is the problem of a single class training, where we only have the safe case to train on. And so what we want to look at is assuming that the dangerous case, which we want never to occur, looks different. Now, if it doesn't look different, we wouldn't find it no matter how much training data we have either. And we will also find crazy people as well, or sick people, or things like that. We have to be prepared that we will find many kinds of anomalies, not just the one kind that we thought that was in there. But that's exactly, in fact, I was in Israel not so long ago, and they asked me specifically if this could be used just to look at people's motions and see if there's an anomaly. You know, if you look at a shopping center, everybody walks this direction at one time of the day, different direction, different times of the day. They don't stop in certain areas and then rejoin, or they don't go crosswise, or they don't stay stationary at closing time in the wrong place. So there's a lot of that sort of thing that you could do without the positive, unfortunate training data that you might have. Anomaly detection is all about finding, as the title suggests, what you didn't know to ask for, what you've never seen before. So this is the method that you would use for exactly that case, because you don't want any training data. Yeah?
I was thinking about the frequency domain as you're doing all this, and you mentioned Fourier transforms.
He insists that he has Fourier transforms in his head. But okay.
I was wondering if why you say the Fourier transform is no longer being used.
Well, I haven't done the work, so the reason I say that it's not being used is because people who did the work told me that. You know, this is kind of a vacuous thing on my side. The reason that they decided not to use it is because it takes battery power to compute it, and those systems that use hand-built acoustic features using Bell-Kestrel coefficients, you know, where you take the Fourier transform and take the transform of the transform in order to see harmonic structures and things like that, do not perform as well as the deep learning systems. It's a very, very pragmatic thing. It's money. And a system that doesn't work as well and that eats your battery is not as good, and people will not pay for it.
So this is actually less expensive to do several levels of deep, several layers at the time series level rather than doing one transformer.
It is certainly much cheaper to do this than it is to do this and Fourier transforms. So, you know, this doesn't need those features. It works very well without them. And so to do the Fourier transforms and the Kapstrel coefficients would be adding computation to this. So of course that would be more. But in fact, from what I hear, it actually is more efficient. And the fundamental reason for that is probably, I don't know for sure, that the Fourier transform finds you samples that are evenly spaced in frequency.
Yeah.
Yes, well, not just periodic signals, but the frequencies that it pops out with are spaced at constant frequency intervals, which is bad if you have ears like ours that do not hear 10 hertz differences in kilohertz signals, but we do hear 10 hertz variation in 100 hertz signals. We hear relative frequency, not absolute frequency. The Fourier transform is an absolute frequency transformation. And so it is wasting enormous amounts of computation, computing very, very fine gradations of high frequency signals, just so that it can understand the low frequency signals. And you can build cascaded things and go through enormous efforts. You can do you know, various kinds of wavelets that are multi-timescale and so on. It's quite a lot of work to try to come up with signals that do not compute equal frequency resolution across the spectrum. And this inherently has variable width and variable resolution at different parts of that. And that alone makes the time domain computation at least as cheap as the FFT. FFT has the n log n sort of cost instead of n squared. But the fact that we don't want all of the frequencies means that the time domain computation without the regularities that we use doesn't have to have n squared. It too can have n log n cost.
This gives you variable size screen windows.
It gives you whatever sizes are good. Yeah.
Whereas the Fourier fixes you with fixed size
Lockstep.
discrete windows. You don't care about half of them. You only want 10 discrete windows and give you 100.
But no, it's not that you absolutely don't, you know you don't care, not just about half of them, but it's 99% of them. And so it's an enormous cost to compute that at this resolution you want. You can decrease the resolution in some frequencies, increase it in others by these techniques fluidly, very, very cheaply. So that's why these are power competitive, is because they don't necessarily compute all frequencies at the same resolution.
How do these adapt over time?
You retrain them.
You just constantly retrain them. The periodicity of a heartbeat. You don't care.
Excuse me. How does the EKG thing adapt over time? Well, you would train it on a lot of data that a lot of people have heard. I don't know what's the past tense would be. Should be butt, right? Heartbot, or whatever, heartbot, whose hearts have beat.
I guess what, in the case of
Those people
the
have
heartbeat,
fast
you know
and
that
short.
if you're running, normal is different from if you're at rest, and it changes slowly, so you.
Right, and so what it's going to be doing there is it's going to be saying, oh, fast pulse. Therefore, I expect fast pulse. I don't expect it to stop. I don't expect it to suddenly stop, slow down. I expect it maybe to slow down slowly, maybe increase just a little bit, but pretty much stays steady. And then waking up in the morning, you got a 50 pulse or whatever. I expect it to be fairly constant. It might go up fairly quickly, but not too quickly.
But over time, you have a trailing window where you're using to train.
Inherently, you
to retrain
have
the
a
system.
trailing window because these higher levels are saying, here is fast heartbeat, there is slow heartbeat, and they can't be too different. So it will learn those kinds of constancies. So this is really cool. I mean, we've already come to where we can see anomalies. We can find semantic things about the signal out of this anomaly detection framework. what about how do we store this? Well, we also had compression along the way. And so the idea of storing this in a database, we don't actually have to keep the original signal if we don't want to. We certainly don't have to keep the reconstruction of the signal. We might keep the original, or we might just keep the interior values, which compress the signal massively, plus the reconstruction error. It's a very effective compression method. But the other cool thing about it is that those interior nodes, which are sparse, are the sort of things that we can index. So we could actually have semantic search for free in a time series database that is also highly compressed. Highly compressed means between 10x and 100x for common signals. And so this is really kind of exciting to have compression, database, and semantic search all built into the same framework across a wide variety of signals. Now, building it and actually running it requires that we look at real time for the actual signal processing and long time to build the models, and we have to match them up. We have to make them coordinate, and I've talked to other places about extended lambda architecture and ways to do that. I think that the MapR system, again with Red Hats, is a great way to do that because it has a real-time file system, but somehow you always have to get that real-time glued together with long-time accurately and cleanly in order for these systems to work effectively. So feel free to ping me about details that I've elided here. The code's available on GitHub. You can reach me by email, by Twitter, by all kinds of things. But I'd love to hear more about the signals you guys face, or the problems you face, or what you'd like to do with this. If we used up all the questions already, surely not. If not, I will cite them. Oh, the man rescues you all. Okay.
Yeah, the slide you had on deep learning, I'm a little unclear on one thing.
Well, no doubt, I had a slide on deep learning,
Yeah,
whereas other people give entire courses on the subject.
So you go from your original signal to sort of a basis of reconstruction, and then you go to that second layer of abstraction. How do you determine which basis elements map to the new basis? Does that make sense?
Well, I hear a hint of 19th century mathematics about you. You say basis.
You're using these as function, as small pieces.
As a way of describing it, but it is not a basis in the sense of a minimal orthogonal representation.
Right.
It is massively overcomplete.
Yeah.
It's not orthogonal at all because it's overcomplete.
Okay.
It
yeah.
happens to be appropriate only for the signals that I've been looking at. So
Yeah.
I'll say basis fine, as long as we're not
Yeah, we're on the
thinking-
same page, I think.
Yeah, okay, good.
I just don't know what else to call it.
It's a fine thing to call it. I call it a model because I come from a more statistical background,
okay.
but basis is not a bad place.
How do you go from the one layer of abstraction to the other? How do you take these pairs of elements and map and put them over to another? Do you
Well,
yeah.
it's the same process. The one of n encoding for each window,
Yeah.
I have a sequence of those one of n signals.
Oh, I see.
And I just learn an autoencoder for those.
They were sequential. Yeah, cool.
Bam.
That-
It's the same thing that over again.
Cool.
Turtles all the way down, or all the way up, depending on which way you go. But yeah, it's a remarkably simple thing conceptually. Now, it's not as simple to build. And traditionally, these things have been very hard to build, despite from 1986 or 84 with the original PDP book, the original neural net books, or even from McCulloch and Pitts in the 50s, until a few years ago is how long it took very smart people to figure out how to learn these. And the problem has always been with deep neural nets is the error signals at the top, at the highest level of abstraction. And that gets spread at each level. So by the time you get down to the lower levels, you just have mush. And so it just kind of goes this way, this signal epoch, it goes that way, and then it goes this way, and it averages out not learning anything. And that is the trick. And the trick to that learning has been in several There's several forms of that. One is that sparse coding at these steps has been very helpful. That's a form of very, very rigorous regularization. In addition, non-hyperbolic tangent response functions have been very helpful. They often use what are called rectified linear units, which are 0 for negative values and X for positive values. The nice thing is they keep getting bigger, and so they never flatten out again, so the gradient never goes away. Combinations of these techniques and dropout learning and a few others are what has really changed the learnability of these things. So the question you asked was very specific to what I was doing, but it is the fundamental question. How do we learn these higher level levels? And that is the key question, yeah.
Just to try to connect this back to Mahout, are there specific features implemented in Mahout to make this type of system easier to implement? If I was doing windowing and...
Along those lines, actually, I was going to ask a related question, which is, I know Mahout's at 0.9 right now, but if you could talk a little bit about the roadmap to 1.0.
Yeah.
Since we are heavily enterprise stable software community.
Well, I'm tempted to answer the standard sort of answer at this point in the talk, which is yes and no. But the actual answer is a bit different. It's no and yes. There's nothing that Mahout does better than other systems to make this sort of computation easier. On the other hand, the EKG thing is something I did code in Mahout. So obviously it had something in my head that made it easier. It has a very flexible and simple math library, and that's what I used to encode the learning law there. But for the real deep learning stuff, the amount of math and the density of the math becomes inappropriate for the Mahout math library. What Mahout does very, very well is recommendations, and this is very far away from recommendations. Right now, the most accessible systems that I know of for deep learning are one called Caffe, or a different implementation called Decaf, both from Berkeley, which is focused around visual learning, and a commercial open source system called H2O, which has a deep learning implementation. Now, I would tend to go with the H2O, partly because I know the guys, but partly also because they have a bit more of a commercial focus than a research focus. So therefore, it's in their interest to make it easier for you to use it. The researchers, it's in their interest to make it easier for them to use it. And that difference makes all the difference some days. It's a huge difference in motivations that leads to a huge difference in the style of code. The academics just have a different mindset and goal set. H2O is very efficient and very nicely parallelized. Their CTO is a guy named Cliff Click. I like to joke with him that he clearly the secret inventor of the click-through rate, but he insists not. What he is the inventor of is he did the first implementation of the Java just-in-time compiler. So he does know how to make Java run really fast. And he built a distributed computation framework. And then Arno Kandel is the guy who works at Hexdata, who implemented this particular deep learning system. And he has a history of building very, very effective machine learning systems. An ex-physicist, but very, very good.
I think that gets mine. So I'm very curious about his answer as well. With where's the
roadmap to Mahout's 0.9 right now with those official release. The roadmap, actually specifically two questions. Number one is a completely loaded question for me, which is when are you going to have a release that supports Hadoop 2? It's actually a release. I know Master will do it. In fact, my Stack Overflow answer I think is the number one answer on how to build it.
Yeah.
But then also a roadmap to 1.0.
Yeah, so the roadmap relative to Hadoop 1, Hadoop 2 is we don't care in the future. Because the differences between Hadoop 1 and Hadoop 2 have mostly to do with MapReduce,
Which you're already seeing.
which we're leaving behind. When Mahout started, which was a remarkably long time ago when I think about it now, 6 years ago, about the same time that Hadoop started, MapReduce was the only game in town for scalable computations. But it is definitely not the best for the kind of computations we want. The future of Mahout is in a language that we're building as a domain-specific language on Scala for expressing mathematical algorithms in relatively mathematical terms. And then that compiles in a lazy way into any of a number of backends. The current two supported backends are Spark and H2O. And so, assuming we continue, which is always an open question with open source, that's where we're going to go. Already the recommendation that the key, so historically Mahout supported every frigging recommendation algorithm out there, most of which were just horrible, and their only virtue was they were mentioned once in the literature. Of these, there are two classes that matter in terms of actually doing recommendations. One is the simpler, and that is co-occurrence based, which things occur together more than you'd expect. Well, that means that they probably are indicators for each other. If one occurs, you can bet the other was shortly behind it. And that is very easily deployed with the search engine, and that has been implemented already in this different.
I'm going to exchange emails with Pat about these blogs.
So you're very familiar with that. It isn't ready for prime time at this point, but we're working to package it up so it'll be much cleaner and much easier than the old Mahout stuff was ever to do. It also brings in new capabilities for cross-domain, multi-action type learning. You can imagine the importance of that is if you're thinking about razor blades or DVDs. With razor blades, if I bought the same exact razor blades before, that's a great indicator I'm going to buy those razor blades again. If I scrolled down the web page and read all the reviews, that's a great indicator of something else. It does not indicate I'm about to buy it. It might mean I work for the company, it might mean I'm crazy. But it doesn't mean I'm a normal razor blade consumer. On the other hand, if I scroll down to the bottom and read all the reviews on a DVD, that's a very good indication I want to buy it. May not, but for whatever reason, but I probably want it. Whereas if I bought it before, I'm probably not going to buy it again. These are different actions which have different implications and are different indicators for different items. You cannot smash those together, which all other recommendation systems do, and still recognize their distinctiveness. And the new Mahout implementations do that. They keep them separate and let you recognize that. So that's a big deal. And you literally can build these systems and deploy them in a matter of hours to days. We've had people, I showed this, and even before there was any software available, I showed them on Friday, and on Monday they had a prototype running. And in a few months they had it in customers' hands. So it's very quick to do. The other style is the matrix decomposition style. It's useful for a few kinds. It is very rare for the decompositions to outperform the co-occurrence-based stuff. The places it does is very small data examples. But I always recommend the co-occurrence now, just because the performance is usually better and the ability to use multiple lines of evidence is so big. And I find there's a huge value in getting something run quickly and then spending time on getting better data or building a better UI. You should not spend your time on algorithms with recommendations. You should spend it on understanding of users and your products. That'll give you far more bang than tweaking an integral sign. I mean, I speak as a guy who does math, and I say, don't worry about it. Yeah.
Where do you see, with the Spark bindings being developed right now, where do you see the division between the mlib, which comes with Spark, and what Mahout provides?
I don't know, Jean-Louis of Databricks and I have talked about this. Right now, MLlib is kind of where Mahout was a while back, where everybody's kind of just doing their favorite algorithms. There's no sense that there's a core task or a core resultat, a reason that people are doing this, and there's not necessarily a sense that most of the contributors will be around later. In Mahout's case, it meant that 80% of the code was stuff we were willing to delete. And we will be deleting. We've already deleted a large fraction of it. And I see that same evolution in MLlib is going to happen. There is a core of goodness to it, but much of the code being generated now is, I'm so excited to be part of Spark. And I do machine learning, and that's not high value. I think that most machine learning problems are small. They don't need Spark, they don't need Mahout, they don't need H2O. Unless those have single machine implementations that are very easy to use. Most problems are relatively easy solved with R. And so I think that's a far better solution for most of those. For the scalable things, I think you begin to see applicability of far, far fewer algorithms and far, far simpler ones. And so I'm not sure that the 1,000 points of light blooming is, to cross metaphors between George Bush and Mao, excuse me, I don't think that those are necessarily a grand thing to be happening. It's a good thing to do, but I don't think it will necessarily serve the project well in the long run. But we'll see.
No.
And could be that we work together, could be we diverge and specialize in different ways, could be a lot of things happen. And it is open source. If Mahout comes up with a wonderful and brilliant idea that doesn't seem to be going somewhere, I'd be thrilled if MLlib stole it and vice versa. That would be fine. All of those futures are good because it's all open source and it's all about whether or not the community is served. And I really don't care what we call it. I guess that's a long way to say I don't know. Okay. Should we just gather back around and talk more informally? Yeah.
I wanted to pick up a book on this. Where would I start?
What's this?
This deep learning.
Well, the deep learning, I'm sorry. Maybe if you'd said Anomaly Detection, I could say you get a free one.
Actually, Anomaly Detection. Let's go with that.
Yeah, Anomaly Detection, there's a nice thin book that describes all these examples in detail, plus a few others. Ellen and I wrote it a couple months ago, and it's available on the MapR website. Just ping me and Friedman and Anomaly, and you'll find the landing page for that. Or send me an email. And
Is that PDF also the one that's been advertised on Twitter?
Yeah, O'Reilly's selling it now.
Okay.
There's a little bit of confusion here. We can still give it away, but they're selling it. It's fine if you want to buy it. I get royalty, or I don't get it. Ellen does. I gave up the royalties on this. But I'll give it to you for free too. I mean, I don't know. I'm confused about that. Conflict of interest everywhere. But yeah, you can have it. For deep learning, there are no books yet. No good books. There's a lot of very interesting papers, and I could send you a pile of them.
Okay.
There's a good Stanford website, which is Deep Learning Tutorials, and that's a very good site. But I don't know of any good books. And I think that the first 24 books that appear on the subject are going to be unusable, because they're going to have one particular mindset rather than other. There's a very, very good survey article by Sammy Benchio, but it's still pretty oriented toward research problems rather than real life. So.
Just to build on the question, so are we pretty far behind, or beyond like the Mitchell book, which is kind of the classical machine learning book, with where we're at with deep learning? I mean, or is a lot of this kind of built on top of that?
All of the concepts, I'm not so much, I don't know the Mitchell book, but the Chris Bishop's book is the one I like.
Okay.
It's still totally applicable. It's all about doing math well, but that is not where most users of this need to be. That's where people who are inventing new algorithms, testing them, need to be. And that is a sign of an immature software, as if most people can't use it because they don't have PhDs. I've got a PhD, but that doesn't mean I'm like everybody else. God forbid. And the software becomes usable when it can be understood at a different plane of existence, where you're in the problem space rather than the implementation space. And that isn't there yet.
I have a question that has nothing to do with the material you talked about tonight. And if anybody else has questions about...
Just ask it, let's go.
Okay. Given that this is the job of the Chicago Job User Group, and given that you've mentored a number of Hadoop type projects, I have a question about trends that I've seen in some of the newer code in the Hadoop software stack. There seems to be this new trend in creating structures, not creating open structures, creating new structures that have that last argument before you. And the last argument is interface that has there is an interface called options that doesn't actually have any methods. It's just there so that somebody can say, is this an instance of that interface? And then there's frequently a convenience method somewhere built in that checks a case test. Am I this version? Am I this version? Am I this version? Maybe I'm a grumpy old man, but I feel like that's usually not a good option. And I'd love to hear your thoughts on that.
If it's useful, it's a brilliant convention. If you look at the latest NIO stuff, the way you deal with files, it's beautiful, the way you do it. I mean, if you're going to open a channel and you want to say readable and it's writable and create it, then it's great just to say, here's 3 options about it. And it looks nice, and it's much nicer than the magically they're binary things that you have to know you can add, or maybe you can order, but maybe you can't add. You know, like, who knows?
Part of the point is not to have 10,000 constructors, so you want to have one that has lots of very wide.
And then the other style is the fluent constructors, where you have dot set such and so dot something else. And it's very much like Wava's splitter and things like that. That's beautiful when used well too, but both of those are shiny objects, so you know they're going to be used in 100 different places really poorly. And just documenting is important, but also just don't just use things because they're shiny, especially in code other people have to use. It's fine to do it in your own code, learn what works and doesn't. But frankly, the average level of it's a very sad thing, but it's also a beautiful thing. But in wide open source, the average level of contributor is kind of average, because anybody can contribute. And that means the average code quality in things like Hadoop is generally kind of abysmal. And the trick is building systems that survive that and flourish with that. The virtue of certain proprietary sorts of development is that you can make gorgeous code that's just fantastically well constructed and high performance, and that but it would never survive average people contributing to it. It would just be disastrous. But the other problem is that you can't necessarily attract the incredible superstars to contribute to the general open source. I think most of the instances in Hadoop are not well done. They're certainly not thought through on the level of like the Guava libraries, where they think very hard about these things, or the NIO library coming in Oracle. Those are very nicely done. And yeah, I'm pretty grumpy too.
Just kind of even building on that question, I mean, with Mahout being an Apache project, what do you see between kind of the GitHub model of open source versus the Apache? Does Apache still have anything above and beyond that of what the GitHub model has, or would a lot of projects be better served in?
That's a great question, but people forget that Apache model was never about the source code control. It was never about anything except building a community and building in guarantees. And the guarantees had nothing to do with function. Guarantees had everything to do with it being safe for businesses to use. Old motto of Apache was business safe open source. And that is in opposition to things with viral models or loosey-goosey dependencies. Drill is a relatively new project. It's not aggressive about excluding or including dependencies. It has over 100 dependencies. Mahout has over 100 dependencies. Do you want to go look at the license to every frigging one of those and determine whether or not it's safe for your business? No. Do you want to look at every one of those and determine that regardless of what the people said in the license, would they sue you for using the software they released as open source because that's a patent infringement? It's just a nightmarish scenario for anybody who has to go do that checking, or for their supervisors who has to certify that, oh yeah, it's safe, we're betting their business on this risk, and it's just fine. And the goal of Apache in many ways is to ameliorate that risk. So the crux of the Apache license is not you can use the software. The crux is in clause 4, which says that you hereby license all patents that you may have that are represented in this code. And your license to use Apache software expires, expunges, goes away if you sue anybody on the basis of Apache IP. So if you have a patent and you sue him, but you put something into Apache based on that patent, you lose the right to use Apache Web Server and everything else by suing him over that patent that you own. Mutual assured destruction. That's the crux of Apache. So now the question you gave was, does Apache bring anything over GitHub style open source? I'm damn straight. And it is exactly the thing it brings, which is exactly why it is slower and more painful to develop. So your virtue will be your vice will be your virtue. Exactly what holds here. GitHub is quick and easy and fun, and I use it a lot. And God help you if you find a project out there that has 100 dependencies on it. You have no idea what you're doing. Apache is a pain in the ass many times. We just did another release on Drill and they got it all right. But it's pretty damn amazing what you have to do to get that right. And then, therefore it's painful, but therefore it has virtues in terms of licensing. There's a huge difference. And neither one is wrong, neither one is right. They're both fun. They just do different things. It's a good question, very good question. And one that people just don't get.
Yeah.
Yeah, they just have no clue. So it's very important to mention in public. Should we just get it? I don't have to fly out of here till 9 tomorrow morning, so if anybody wants to wander to a pub nearby or something, we can do that. He thinks so. Okay, let's do it.